Hello. Okay. Hello, everybody. I'm sorry, keep you all waiting there. Just some technical hiccup, but we're good now. So my name's Aaron, and good to see everybody today. Just want to welcome you here to Go to 10. For those who have not been here before, you're very welcome. A little bit about Go to 10. We are non-profit organization run by this crowd, Internet Stiftelsen, the Swedish Foundation for Internet. And Go to 10 is one of their programs to promote innovation, entrepreneurship, knowledge sharing. And we are a free space for members. If you're a member, you have access to this place for free. And you're welcome to become a member today and use this space. We're open Monday to Friday, 8 till 4:30. And there's no cost involved. So you're very welcome here today. And if you have any questions about the space, or if you want to have a look around and see what you have access to as a member, please talk to me and I can show you around. But now I'd like you to pass to Anna, who's going to introduce today's event. Thank you.
Thank you, Aaron, and we're so happy to be able to be here and to use the facilities at Go to 10. My name is Anna Broders. I work as a talent and community manager at Linköping Science Park. And today's event is TechTuesday, which is arranged by 5 of the companies and us, Linköping Science Park then. And the companies who are behind TechTuesday are Ericsson, Near Dynamics, SICK IVP, Combitech and Sectra. And today we have, as you all see, SICK IVP with us as today's host. And the speaker, Johan Melander, will talk more about CMOS. He just learned me that's how you pronounce it. Image sensors, which is a technology evolution. So Johan will do his speech, and then afterwards we have time for questions. So please prepare questions, keep them in mind, and we'll take them after the speech. So Johan, the floor is yours.
Okay, so we are really close together here, so I really don't need this, but it's for the live streaming, I've been told. So I'm not really used to talking into a mic, but I guess it will be okay. So, and I've been told to stand here, the camera is there, but I need to progress my presentation, so I will go back and forth here. So, nice to see you. A few familiar faces here. I will talk about CMOS image sensors and technology evolution. It's quite a niche technical topic, but I think I will be on a level that will be understandable. Okay, so let's go. The agenda for today is the image sensor technology that has enabled SICK to build one of the world's fastest laser triangulation cameras. That's basically the agenda, and will be the red thread through this presentation. So my name is Johan Melander. I'm 54 years old. Graduated from LiU, from a master's in computer science and electrical engineering. And at 97, a LIS engineering degree from Department of Electrical Engineering, also at LiU. After that, I started to work for a LiU spin-off company called named Integrated Vision Products, IVP. IVP was actually founded by Robert Forsheimer, which is a famous name in this area, and Anders Ödmark already in '85. It was founded around this very special idea of a very special CMOS image sensor. And on that track we are now. In 2003, IVP was fully integrated into the German industrial sensor company SICK AG. SICK AG, which was one of the companies Anna mentioned, has around 12,000 employees and sales of over 2 billion euros. So it's a very big company. So IVP was integrated into SICK, and we now represent Innovation Center for Machine Vision within SICK. And we are located here on Wallenbergsgatan, and we are about 80 full-time employees. and consultants and master thesis workers, etc. So, why talk about CMOS image sensors? At SICK, among other things, we develop 3D cameras for industrial automation. Specifically for the products named Ranger and Ruler, we use the laser triangulation principle. And what is that? It's shown here. We have an object, in this case this green truck is moving through a projected laser line. This is a laser projecting a laser line, the truck is moving through it. A camera, this blue one, a Ranger in this case, is set up at an angle to register the laser line. And given the geometry of this setup, the height of the object can be calculated from the laser line. And what you do is that you put several of these height profiles together, you send them out from the camera, and you put them together and you get a height map of the object that is passing through the laser line. So this is the laser triangulation principle. And if you do that, if you, for instance, scan a PCB with a kind of small field of view, you can get these fancy pictures with the height data color-coded, and in this case also the grayscale image overlaid, so you see the text. You can rotate, zoom in and zoom out, typically in the tools that we have supporting these products. So what about the image sensor in a laser triangulation setup? The image sensor sees the laser line, so here it would be the ground level, this is the roof level of the truck, and here the ground level again. Of course the image sensor sees the truck as well, but for this to work, the laser intensity needs to be the strongest intensity in the image. So this is just highlighting the laser line, but in a very diffuse background, the truck is also there, of course, but you need to be able to extract the laser line. So looking in one column of the image sensor, finding out where the laser line is in each column, that position will be proportional to the height of the object that is passing through. So what this really means is that for each column you need to find the position of the laser line, and then you get your height profile. So then to build a laser triangulation camera in a brute force way, the naive way, would be to put in a standard 2D image sensor that delivers these 2D images to a number crunching big FPGA that will, for each column, find the position of the laser line, put it together, put it on a protocol, send it out, and this profile train to the receiver, and the receiver can reconstruct the height map on the receiver side. So what is the problem with this? I will tell you. This is the problem. High performance laser triangulation system would like to the customer needs a 3D profile rate in the tens of kilohertz range. So for instance, a 30 kilohertz profile rate means in this case that you need a 2D image sensor capable of 30 kilo frames per second. And that is really something that is very hard to find or not possible to find at all on the market. So what can you do about it? You can do what we do at SICK and started in IVP. The second alternative, to have on-chip data reduction on chip instead. So this on-chip data reduction will find for each column where the laser is detected, and instead of outputting a complete 2D image, it will instead output this 3D profile. So for each column, only one value, not all the pixels in one column. So the SICK approach then for a laser triangulation camera would be to put this special type of image sensor with the on-chip data reduction sending out a 3D profile instead of a complete image to a much smaller FPGA because you don't need all the number crunching. And then sending out the profile train to reconstruct your height map. And this is what enables us today to do the fastest and most compact laser triangulation systems in the world or on the market. And that is why I today talk about CMOS image sensors, because the technology that enables this. Okay, first a few words about the CMOS image sensor market. Where do we find CMOS image sensors? Number one, with a huge margin, are the smartphones. There's over 1 billion of smartphones in the world, and the average number of CMOS image sensors in the cameras in the smartphones now is around 3, I would say. So there's a lot of CMOS image sensors out there in the smartphones. On the second place, on a strong upward trend, is automotive. There's a lot of cars out there as well, but it's not until recently there is a lot of CMOS image sensors within the cars now. You have this parking assistance, interior view, road sign reading, and so on. It's coming more and more, so this is on uprising. And on the third place is surveillance. In today's society, there will be more and more surveillance. And on the fifth place, we find industrial, and that is where we are with our laser triangulation specific sensor. So dominated by smartphone image sensors. Who are the companies doing this? On the first place, Sony. Second place, Samsung. Third place, Omnivision. And this market is really dominated by Asian companies. If we look at Sony, which is Japanese, we also have Hamamatsu, Canon, Panasonic. On the second place was Samsung, which is South Korea. We have SK Hynix as well. And on the third place was Omnivision, which is China. We have Galaxy Core and SmartSense. And it's not until the 6% of the market, Europe or US, comes. So here we have French, Italian, STMicro. We have onsemi, US, and Teledyne, US. So it's market really dominated by smartphone image sensors and Asian companies. So market dominated by that. So what does the customer expect from a smartphone? They expect it will replace the digital still camera. The smartphone should be enough for taking very good photos. And at the same time, the customer wants the cost and the form factor of the smartphone to be kept. And what does that mean from a technology point of view? It's a really tricky design due to the extreme space constraints for the optical design. The image sensor size cannot increase. And what does that mean? We want a better image quality, we want higher resolution, and if we cannot increase the image sensor size, we need smaller pixels. So smaller pixels is the key here. So a small high quality pixel has now been the driver for CMOS image sensor technology for many years, because the huge market and the constant drive of getting better and better image quality in your phone that you have in your pocket. Okay, to enable this then, to make small high quality pixels, we need a specialized CMOS manufacturing process. Why do we need that? A standard CMOS process is what you use to, for instance, manufacture the Intel CPU or the Snapdragon from Qualcomm or an Nvidia GPU. The process is optimized for logic. It scales with Moore's law still, even though the scaling is not the same as it was 20 years ago. And the state-of-the-art process is now at 3 to 5 nanometers. This shows a cross-section of a standard logic process. We have the front end of line, FEOL. It's the silicon bulk where you do your devices, transistors, diodes, etc. You have the back end of line where you do your metal wiring and interconnects. We have the front side, the back side. And the starting material for all this is the silicon wafer. I'm sure you have heard of that or seen it. And when you have a ready-made product, you package it in a typical package like this. Example, an Nvidia GPU. It's completely covered, no light comes in. Okay, so this is a standard CMOS process. And the CMOS image sensor process is a process where you have it's very similar to the CMOS process, but you have very specialized process steps to accomplish image sensing. So a few things that is obvious is that you need a photodiode, a light-sensitive device in the silicon to be able to detect light at all. You cannot do any metal routing on top of this because that would block the light. That is obvious as well. And the package, you cannot have the same package as the Nvidia GPU on the previous slide because you need a glass lid on top of the silicon instead of covering the silicon with metal or plastic because you need the light to come into the photodiodes. So these are 3 obvious things. So besides this, what are the most important process step in a modern CMOS image sensor process? That's the reminder of this talk now. Before I start to listing the 6 most important process steps, I want to introduce 2 key concepts to explain why these 6 process steps are the most important. Is crosstalk and full well capacity. So what this image shows here is a cross section of 1 pixel. This is the front end of life, the line, the silicon bulk. Here you have your photodiode and you have your pixel transistors. Typically you have 3, 4, 5 transistors in the pixel, but in this example I only indicated 1 of them. On top here is the back end of line with the metal wiring, and as you see there are no metals above the photodiode here. And the light detection principle is that you have a photon impinging on your device, on your pixel. The photon can generate a photo-generated charge, electron or hole, being an electron in this case. And this electron can be collected by the photodiode. Now the concept of full well capacity is how many electrons can I collect in my photodiode. When you reset it, it's empty, 0. And then as photons impinge on your pixel, it will fill up. And in this case, we have a full well capacity of 80,000 electrons. That's very big today, I would say. But it means that you can collect 80,000 photo-generated charges in your photodiode. So that's full well capacity. Crosstalk then. If a photon comes in at an angle, it could, for instance, in the back end of line, hit the metal wiring and bounce and end up in a neighboring pixel. So this would be optical crosstalk in the back end of line. That is in the metal part. And then you can also have the optical crosstalk in the front end of line. The photon can penetrate down in the silicon, go over to the neighbor, and generate the electron in the neighboring pixel instead. And then it's named optical crosstalk in the front end of line. And the second, or the third part of crosstalk is electrical crosstalk in the front end of line. So a photon could generate a charge in the correct pixel. The charge is generated, but it diffuses to a neighbor instead of being collected in the photodiode. So that's another type of crosstalk. And this crosstalk, depending on how pronounced it is, will deteriorate the image quality, of course. So what happens now when you shrink the pixel pitch, when you make smaller pixels? You remember the key was small, high quality pixels. If you shrink this and go to a more modern process, we end up with something like this. We have a higher number of metal layers because this is a more modern process. Due to the shrinked pixel pitch, the pixel is typically quadratic, so the sides of the pixel are the same. If you shrink the pixel now, you have less volume for your photodiode, so your full well capacity will go down if you shrink the pixel, and that is not good for image quality. Also, the relative impact of the crosstalk, both in the front end of line and back end of line, will increase because the shrink of the pixel. So that is also a drawback for image quality. So what this boils down to enable a high quality small pixel is to maintain a good enough full well capacity and also to reduce the crosstalk. So all the technologies that I will show now, 6 of them, are introduced to fight that we have a good enough full well capacity and that the crosstalk is completely eliminated or at least reduced to a high degree. So the first one, already in the early 90s in CMOS image sensor, is the concept of micro lenses. It is just what it says. It focuses the light to the photodiode with the use of a lens on top of each pixel. So the principle is really easy. Here's the example without micro lenses, and here is the example with micro lenses. So on top here you have a micro lens on top of each pixel, focusing the light, directing it to the photodiode, increasing the probability of detecting light in the correct pixel. So in the early 90s, pixel sizes were larger than 10 microns, and this technology reduces crosstalk, less light is wasted. So this is the first key technology. The second one is the introduction of the pinned photodiode. This was seen in products in mid-90s, 95. It's a pixel structure that was inherited from the CCD imagers. It requires carefully engineered process steps in the front end of line in the manufacturing process. So it's a tricky thing to introduce, but the pin photodiode gives you a high quality photodiode with a low noise, and the low noise enables you then to maintain your image quality even though your full well capacity shrinks. If you have a big full well and quite a big noise level, then your signal to noise ratio would be okay. But if you shrink your full well capacity and still the noise level is equally high, then your signal to noise ratio will be too bad. So with this photodiode type, the pinned photodiode type, you get a low noise pixel, enabling a good image quality with a lower full well capacity. And I will not going into the details here, but this is a typical 3 transistor pixel that was used before you had the pinned photodiodes. You have 3 transistors in the pixel, you have your photodiode. And with the pinned photodiode, you introduce an extra doping layer on top of your photodiode, and you separate your photodiode from your sensing node with this transfer gate. So this is, you can see it as an extra transistor in the pixel. It enables, when it's closed, the photodiode is separated from the sense node, and when you open it, you transfer your collected electrons or your collected photo-generated charges from the photodiode to your sense node. And there's really a lot of technical stuff around this, but this is what I will say about that. And this is the second technology, really important. Every CMOS image sensor uses this kind of pixel. 95, we were at 10 microns. And this technology gives you maintained image quality with a lower full well capacity. Okay, so the third technology then is backside illumination, BSI. This was first seen in products in 2009. It was regarded as a disruptive technology, disruptive because it took a huge step forward in the possibilities of CMOS image sensors. On the left-hand side here, you see a front side illuminated, what we used before, backside illuminated. You have a front end of line, your pixel and your pixel transistor, your photodiode and your pixel transistors. And you put your back end of line here, your routing, and you put your micro lenses on top. And the light penetrates here, reaches your photodiode. This is front side illumination. Now, backside illumination. You simply take this, not the micro lens, but you take the front end of line, back end of line, you flip it upside down like this. You add it to a silicon handle to be able to handle this in a stable way in your manufacturing process. You thin it. So there's maybe just 5, 6, 7 microns left here. That's really thin. And finally, you put your micro lenses here on the back side of the silicon, because this was the front side, right? So that is why this is called backside illumination. And how does this help? Well, first of all, the light does not at all go through your back end of line, your metal stack, right? So you could use your metal stack for easier routing. It will relax your routing problem. And you completely eliminate the crosstalk in the back end of line, because the light does not shine through the back end of line. So removes the metal wiring part from the optical stack, eliminates the crosstalk in the back end of line. And 2009, pixels had shrunk to around 2 microns and eliminates the crosstalk, easier metal routing. So this was really a big step in CMOS image sensors. And connected to this step is the fourth technology I want to mention. It's deep trench isolation, DTI. First seen in products 2010. This is a backside illumination, 3 pixels, backside illuminated. The micro lenses on top. We eliminated the crosstalk in the back end of line, because the light does not go through there, but we still remaining is the electrical crosstalk here, and also the optical crosstalk here. What can we do about that? Deep trench isolation means that you set up sidewalls around your pixels to isolate them from your neighbors in an both optical way, so a photon coming in here bounces sort of on this trench and stays in the correct pixel. And also if you have electrical crosstalk, this electron is not detected immediately in your photodiode. It will not diffuse to a neighbor. It will be kept inside your pixel and with a high probability then be detected in your photodiode. These trenches, it's really amazing how they can be manufactured. The aspect ratio is really crazy. It's like, I heard some analogy where you, with one shuffle, a garden shuffle this wide, would dig 20 meters down. That is something like the aspect ratio that you use here in the DTI. They can be filled with polysilicon, oxide, metal, or even they can be left unfilled, so it's air. Okay, so this is a technique then to avoid electrical and optical crosstalk in the front end of line. So now we have almost completely eliminated all the crosstalk that I mentioned in the start of this. And now in 2010, pixel sizes between 1 and 2 microns, and this technology offers then the less crosstalk in the front end of line. That was number 4, 2 more. Number 5 is the vertical transfer gate, and this is really also a very advanced technology. It takes a lot of careful engineering and process steps. It is important for the very, very small pixel sizes. So it's not used if you have a pixel that is maybe over 1.5 microns big or over 1 micron big. So the vertical transfer gate, the VTG, is a technique to improve the full well capacity when your pixel size shrinks much. As we see in this picture, that is a cross-section of 1 pixel. We have the pinned photodiode. We have the transfer gate that was introduced with the pinned photodiode in the second technology that I mentioned. When you activate your transfer gate, you open it. The photo-generated charges in your photodiode will be transferred to your sense node, and the electrons have a horizontal transportation direction. And what is important to note here is that this volume of the pixel is not possible to use for charge storage. It's not possible to use for your photodiode. So the vertical transfer gate buries the photodiode under the transfer gate and your other pixels in your other transistors in the pixel. So by putting your photodiode deeper in the silicon bulk, extending the gate of your vertical transfer gate down to your photodiode, keeping your sense node here. Now when you activate your transfer gate, the charges from your photodiode will be transported vertically to your sense node. And that is why it's called vertical transfer gate. And this then offers you a higher full well capacity, this technology. So this is without the vertical transfer gate, and this is with it. So it's deeper in the substrate, but you can utilize a larger volume of the pixel for charge collection. In 2013, around 1 micron in pixel size, and this technology increases the full well capacity. The last technology I wanted to bring up is 3D stacking. This is also a disruptive technology. It was first seen in CMOS image sensors for smartphones 2018. 3D stacking has been around for standard semiconductor products before this, but in smartphone imagers first seen in 2018. It is not a technique that reduces the crosstalk or improves the full well capacity. Rather, it offers more performance in the same package. So, having said that, it's not actually in line with the 5 first technologies that I presented, but it's still one of the 6 most important technologies for CMOS image sensors now. And what does it mean? You remember this picture with the backside illuminated sensor. You have your micro lens, your photodiode, your metal routing, and it's connected to a silicon handle. So instead of this silicon handle being a dumb silicon handle, you can replace it with what's often named as an ISP chip, image signal processor chip instead. So instead of this dumb silicon doing no use other than mechanical stability in manufacturing, you can replace it with an own chip, an image signal processor chip. So on top here is the CMOS image sensor chip, and here is the ISP chip. What you also need to enable in this technology is the connection between the 2 silicon parts. And this is illustrated here. It's necessarily not per pixel. It can be in the periphery of the circuits, of course. And 2 main technologies exist for this, is the through silicon vias or the copper-copper direct bond interconnect. And today, these connections can be done in a pitch down to around 1 micron. So it's really possible to have pixel-to-pixel connections today. And that opens up new architectures for CMOS image sensors. So this illustrates the concept. Again, you can have the pixel array on your silicon, you have the logic on the same silicon. If these 2 are equally big, you can split them up and stack them on top of each other. So, yeah, 3D stacking, offering more computational performance in the same package. So then, what can you use this extra computational performance for? In CMOS image sensors, could be used for autofocus, face detection autofocus. That's common. In your phone, it's color images. I have not indicated any color filters here, but typically between the micro lens and your photodiode, there are color filters in your smartphone camera. And then there is a technique, remosaicing of color images, that is resource hungry, that you can put in this ISP. Computational photography, HDR modes, different advanced corrections, or you could be detecting laser peaks in columns if you do a laser triangulation sensor. Okay, 2018, around 0.8 microns in pixel size. You could wonder, does that make sense at all? You are way below the diffraction limit of the optics and so on, but some people say it's worth it, and some say it's not worth it. But you sell a lot on the company that has the smallest pixel pitch. You can cram the most of the you get the highest resolution on your image sensor, and you sell on a data sheet. It's necessarily not the best image quality, but you still sell. So, last slide. This shows a cross-section of a state-of-the-art imager. It uses all of the 6 technologies. On top, we have the CMOS image sensor silicon. Here we have the ISP silicon. Here is a direct DBI connection indicated, and there is one a little bit deeper down. This is the metal routing part of the CMOS image sensor silicon. This is the metal routing part of the ISP. The ISP transistors is here because this is the silicon bulk. The front end of line, back end of line, connected to the back end of line and the front end of line. It's backside illuminated. You have your micro lenses on top, and this here shows color filters. I have not indicated them before, but in this cross section you see the color filters as well. You see the deep trench isolation, and you really don't see that, but here are the pin photodiode with the vertical transfer gates. And closing into the final notes for industrial sensors where SICK is working. The pixel size is typically between 3 and 6 microns for modern industrial sensors now, and that is huge compared to what you have in your pocket for smartphone imagers. But that has an advantage as well, because the volumes for industrial imagers, as you saw on the previous slide, is much smaller than the volumes for smartphone imagers, for instance. So all the technologies that I presented here, they are now available at a reasonable cost for industrial imagers as well. The exception is this vertical transfer gate that is really only necessary when you have the smallest pixel size and sizes, and it's really expensive step as well. So all these technologies can be used by industrial sensors, even though the volumes are not huge. And this is a photograph of our latest imager for laser triangulation. It's named M30. It has a 6 micron pixel. It uses micro lenses and the pin photodiode. But none of the other 4 key technologies that I presented. But it's in your imagination, you can understand what if you are designing a next generation sensor, it would be there are certainly a lot of these technologies that would be a benefit for us. Okay, that was the last from me. Questions?
Thank you very much for this presentation. I really enjoyed to see, like you mentioned, the technology evolution and going smaller and smaller step by step. Do we have any questions? Yes. We do it in the microphone so they online.
Thank you. So I was wondering, is it possible from the laser triangulation camera to also measure the speed of the object being measured?
Yes, it could be, depending on how the object looks and what kind of processing you do. I mean, you could follow a feature on the object, for instance.
That requires a known object.
Yes.
So I was wondering if it's possible to unknown objects, or do you have to have a speed camera next to it if you have objects with varying speed passing through?
Are you referring to the laser triangulation principle, how we are doing it right now, or do you have a new idea? I mean, the way we do it now, as you say, an object is passing through the laser line, and you need to control, you need to have a knowledge of the speed of the object, because otherwise these 3D profiles will not be fitted together into the height map without distortion. So what you typically have is if you have an object passing on a conveyor belt, then you have an encoder sending pulses to the camera, indicating for instance, for every millimeter, and it comes a tick from this encoder into the camera. So you can tag your profile data with this metadata indicating where on the conveyor you are. So that is how you typically handle speed and the variation in speed in a laser triangulation application.
Okay, thanks.
Thank you. One more question over here.
So this might be based on a misunderstanding, but the full well capacity, when that's reached, is it like reset by itself, or is the pixel spent or some such?
Indeed, there are different kind of image sensors, of course. What you mentioned, resetting yourself when you need a threshold, that is one technique you can use for a higher dynamic range capacity. But typically, in this kind of image sensors, when your full well is full, it spills over and drains out to the void. So when it's full, and when your exposure time has ended and you detect that your full well is full, then you get a saturated value in that pixel.
Thank you very much.
Another question?
Why SICK is not using 3D stacking?
Sorry?
That 3D stacking,
Yeah.
sixth method. Why SICK is not using? Because
Okay, why we are not using it? The image sensor that I showed, that are our latest design, it was designed 2014, 15. At that time, this technology was too expensive. Now time has elapsed, and it's not too expensive now.
okay.
I think it's the last question.
Yes. How long does it take before technology from academia becomes rental? Or, like you said, that 3D stacking took a while before it was not expensive anymore. So how long before something that is discovered in academia becomes, reasonable to produce?
Yeah, I mean the industrial sensor volumes, thousands, a number of thousands, 10,000 maybe per year. And if you look at the smartphone volumes, it's huge. So the smartphone, obviously the most expensive processors are the newest ones, and only Sony, Samsung can afford these. And lagging, I don't know, 5-7 years after would make it affordable for industrial image sensors. Yeah, give or take a few years.
Great. If there's somebody who have more questions, Johan promised to stay a few more minutes, so please go and ask him directly. Thank you very much for your presentation, Johan, and thank you all for listening and giving good questions. The next Tech Tuesday will be the 10th of October, and then it will be Nira Dynamics who hosting, with the theme of Data for Climate Resilience Assessment of Roads. So another interesting topic. Hope to see you then. Thank you very much.
I have an image sensor here if you want to look at it. I forgot to say. Thank you. I turn this off now.